thank you for the opportunity to present the work. I'm very happy to be in Lille and to see the wind tunnel. I was told about the wind tunnel in Lille, so now I've seen it. So I'm going to talk about the transition to turbulence with water experiment in a pipe. This is, in fact, the presentation I'm going to show is a resume, a review of some of the works I've done some time ago, back to the time when I was doing a postdoc in Manchester. And I tried to put some results that were not published yet and some things that I've been doing recently with Benoît Lebon. So it doesn't work. But, so Benoît Lebon was a postdoc with me 2 or 3 years ago, and he did the work on the sudden expansion that will come at the end of the talk. And most of the recent work on the synthetic jet, they were done with Shun Ishizaka and Yuji Tasaka in Hokkaido University. First, I want to say that we live in a society where most of the electricity is used, half of the electricity is used to run electrical motors, and half of the electrical motors, they are used to move fluids, to move fans, to move air, or pumps. And if we, unfortunately, we design our equipments to move water and air on very small pipes with a lot of corners. So there is a lot of friction. And so improving the flow in pipes and reducing friction could play a significant role in reducing our energy footprint and our carbon. So it's very important that we understand this fundamental phenomena. Pipe flow is one of the fundamental flow. So if we understand pipe flow, maybe we can understand other flows. Okay. So the outline of the talk is the following. I will first give an overview of subcritical transition to turbulence in pipe flow. I will tell you that pipe flow is linearly stable, and so to get turbulence, you need to introduce disturbances. Most of the work has been done on jets, push-pull disturbances, and now I'll try to tell you something new about synthetic jets. When you do these experiments with this disturbance, you end up with a finite amplitude stability curve. And I will show you that this finite amplitude stability curve does depend on the type of disturbance that you are using. Most of what I will show you is based on flow visualization. So we will be able to say some of the things we can see about the dynamics of the puff. And we also tested the synthetic jets on the sudden expansion pipe flow. And in this case, the transition mechanism for the transition to turbulence in sudden expansion pipe flow is slightly different. So I will show you what are the differences compared to the straight circular pipe flow. And at the end, we've done also an experiment with, we put a rod in the center of the pipe. And also this changes again the mechanism of transition. And I will wrap up. So pipe flow is a very old problem. It started 140 years ago with Osborne Reynolds. He did a very elegant experiment, I think. At that time, there was no electricity, no pump. So to create the flow, he put his pipe, his glass pipe, on the table, very high on the table, and he uses a tap at the bottom to get a constant pressure. And he put everything in a glass box, and with the inlet made of wood and 3 pipe diameters and some kind of ink. He was able to see. So in the original papers, there were only drawings. He was able to see that if the flow is slow, everything goes linearly. If the flow is a little bit faster, there is some flashes, and the word turbulence didn't exist at the time. And if it goes a bit faster again, you get some random motion. And in his paper, he explains that if the day is very calm, in the morning, the temperature is constant, he can get his experiment to run laminar flow for what we call today the Reynolds number, 13,000. So the Reynolds number, we all use it, is the bulk velocity multiplied by the diameter divided by the viscosity. Really, the level of disturbances in the experiment will dictate the critical Reynolds number. In general, with a reasonable level of noise, in a range of Reynolds number between 2000 and 2700, you have puffs, localized patches of turbulence. And for a range of Reynolds number larger than 2500, you have slugs, which is a growing patch of turbulence. So it looks like that. So these are some movies that I did when I was in Manchester. So this is a typical puff made by flow visualization. We put some flakes into the system, a vertical white light, and you see the puff passing through, and it's intermittent. There is laminar flow and yet another puff. The first movie is at Reynolds number 2000, and there is the bottom movie is at Reynolds number 10,000, so 5 times faster. In this experiment, we've been very careful preparing the system. So initially, the flow is laminar. All the particles move in a straight line. And then after some time, there is a disturbance in the reservoir that will start, and the flow becomes turbulent. So we can get laminar flow at Reynolds number 10,000. And if you introduce the right disturbance, you can get the turbulence to appear. So here are some pictures of the flow visualization at different Reynolds number, 1,000, 3,000. And as you increase the Reynolds number, you see that the scales or the characteristic scale decreases. But this is a matter for turbulent flow people. So I was very fortunate when I did my PhD that the topic was really full of ideas in the years 2004 and so on. So until then, people only knew the basic velocity profile, the parabolic velocity profile, and then there was some ideas that there is some nonlinear solutions. People have proved that there is some nonlinear solutions. But based on the self-sustained process described by Fabian Walef, where if you have streaks along the wall, this will become unstable, and then some rolls will appear, and this will self-sustain. And based on these ideas, mathematicians like Rich Kurzweil and Bruno Eckart, they come up with periodic solutions of the Navier-Stokes equations. These are solutions that are periodic all along the pipe. They were not realistic because they were not observed, but came along some experimentalists, Björn Orff, Jerry Westerveld, and some others. They took the movie of the puff that I showed you before. They did a high resolution, high speed PIV of that time, and they compared the slices of the PIV data shown here in ACE to periodic calculated solution BDF. These are velocity maps. It goes fast when it's blue and slow when it's red. And they said, oh, look, the symmetry that we see in these periodic solutions are also seen in the experiments. Of course, they pick a particular solution, but it created a big excitement at the time. And so these solutions have been thought as solutions where when you have a puff, you have in phase space the trajectory of the lifetime of a puff, is passing through the different states, and they call it the ping pong ball, the pinball turbulent flow. So it was very exciting, and I was hired as a postdoc to do experiments in Manchester. So the experiment in Manchester was a little bit special. It was not a pressure-driven flow, it was a constant mass flux experiment. So instead of create a constant velocity, we used a big syringe, a piston that will fix the velocity here, and then the flow will be created and will be kept constant in the pipe. The pipe was very long, 15 meters long, and 200 diameters from the inlet. You could inject a disturbance, and here is a sketch of the disturbance mechanisms that we use. So we use the different types of disturbances, the jets of different sizes. So here is so this experiment in Manchester was duplicated. In fact, the experiment in Manchester was a duplicate of an experiment that was before in Oxford. And then this experiment in Manchester was then duplicated in Tokyo. And this is the version from Yuji Tasaka's lab, where we have also this play machine that can run along and follow the puff as it travels. So there it's a complicated set of data of equipment, but it works quite well. So this, now I will run about explain you what's happened to a pipe. So let's say you have created a Poiseuille flow. You weighted 200 diameters, the flow is fully established, and you want to get it turbulent. It's not so easy. If you knock on the wall, it will not get turbulent. In fact, you have to, most of the experiments we did at the time was to use a hole through the pipe wall. And here I will give you on the left, I give you what's happening if you do a suction here. Reynolds number is 2000. So if you make a suction using a syringe, for example, you can distort the base flow. Eventually, the base flow will create some vortices in the corners. And then if the distortion is not large enough, the flow will get laminar again. Here, in the second column, the distortion is a bit stronger. You see in the second image H that you created some vortices in the wall, and these vortices created some arms that trigger a puff. So this was for suction. This set of data of photographs here is for jet. Again, on the left side, you see the jet enters the flow, creates some hairpins, eventually interact but decay. And on the right side, you see that the jet is able to create a puff. So there is always a sequence of events, spread of the jet, decay or growth, and the breakdown into turbulence, if any. So we tested different diameters of the hole. So here is the injected flux as a function of the time of the injection, right? We do an impulsive disturbance. So of course, if you make a small jet of 1 millisecond, you need to be at a very high intensity to penetrate the flow and make it to turbulence. So if you are below the line, you are laminar. If you cross the certain flux, you are turbulent. The field symbols are for Reynolds number 2500, and the empty symbols are for Reynolds number 5000, and the different colors are for different hole diameter. So basically, after some time, you reach a plateau value. You need a certain flux for a certain diameter, and the bigger the hole, the bigger the flux to get the turbulence. So based on this diameter and this flux, you can calculate the critical Reynolds number, and you have on the x-axis for the second figure, you can see the diameter of the hole compared to the diameter of the pipe. And so again, you get the stability curve. Here, everything is for Reynolds number 2500. But you see that below this curve, the disturbance will decay, and the laminar flow will be restored. And above this curve, we have a turbulent flow. So we did it for different Reynolds numbers. So here we did for single jets in red, for single jets of a smaller diameter in green, and for 6 jets with a slightly inclined direction. For all these experiments, there were, for each point, we did 40 experiments. So below the line, the perturbation will decay back to laminar. Above the line, the perturbation will trigger a puff. So A is the amplitude of the jet. So it's the flux that has been injected with respect to the flux in the pipe. So you need typically 1% of the flux to be able to create turbulence. So this is for a range of Reynolds number from 2000 to 20,000. So we did the same experiment. So when you inject, of course, you are not conserving the Poiseuille flow character because it's Poiseuille flow plus flux. So then we moved on to some push-pull disturbances where we make 2 holes of 1 millimeter very close to each other. And what you inject, you suck. So to make sure that we have Poiseuille flow without any added flux. We did it for different arrangements, 1 push and pull, 2 push and pulls to try to break the symmetry, 4 push and pulls. This is experiments for Reynolds number 2200. And you see that in this case, the red, 1 single push and pull is the one that gives you the smallest flux to get the transition turbulence. So once we compile all this data, you have here the amplitude as a function of the Reynolds number, and you see that the single jet is in red, and 1 order of magnitude below, you have the oblique push and pull, and they have a slightly different scaling law. Another interesting thing that we've seen with this push and pull disturbance is that the error bars, remember this is an average of 40 experiments, the error bars become a little bit larger, much larger. And in fact, when you do this oblique push and pull disturbances, you get a much more complicated phenomena. You make a much subtle, a much delicate addition to the flow, and this disturbance has to grow, and that's why you get a different scaling. Also, some people in the literature have reported that this boundary between the amplitude and the Reynolds number is the place of edge of chaos and things like that. So this is for the range of Reynolds number between 2000 and 10,000. So these are some pictures of the push and pull disturbances. You see that you inject something. This is the view from the side on the left side, and this is the view from the bottom. And you see the hairpin vortices or hairpin-like vortices that appear, grow, interact to the top wall, and decay and moved into a turbulent path. So these are scaling laws, and these hairpin vortices have also been observed in numerical simulations. The push and pull disturbances is evidence of a slow and transient growth process. So now for the range of Reynolds number between at low Reynolds number, let's say 1,600 and until 2,000, the things are slightly different. So on the top row, I'm showing you the effect of always the same disturbance with an amplitude of 0, 1. And I'm plotting the probability of seeing a puff as a function of the distance from the position where I enter the disturbance. And so the probability of seeing the puff, for example, for 1,620, the probability of seeing a puff 200 diameters from the inlet of the disturbance is only 10%. And of course, as I increase the Reynolds number, the probability of the disturbance to die, to become laminar again, is reduced. So from these probability distributions, we can fit an exponential decay. And from the exponent, we can calculate the half-life called tau. And on the second graph, I plotted tau as a function of the Reynolds number. We did the same experiments again for an amplitude 10 times smaller. And we were very surprised that we didn't get the same quantitative data. We get two different critical Reynolds number. So we use this data that I showed you, the probability of puff to die, as an error bar for this these points here in the lower bound. And with this, we completed our stability diagrams. So these data, the open symbols are the data I showed you before with the jet, and the squares and circles and stars are the lower bound data. They were obtained by the lifetime measurements. So with this, we could obtain the stability curve and for every for several disturbance mechanisms. This type of diagram was also obtained for the from another group in Germany, from the PhD of Nishi in 2009, where they use a diaphragm and they use a compressed air experiment and a hot wire anemometer to obtain this data. And we were quite happy that we had the same lower bound wall. So in their experiment, they looked at the end of the pipe and they checked the occurrence of a disturbance passing through, of the disturbance splitting, and of the disturbance growing at different Reynolds number. That's what these figures on the right side show. To try to have a more definite answer about what's happened at low Reynolds number, we also did a slowdown experiment where we created a puff at a Reynolds number 1,900 by injecting, and with the camera we follow this puff. This puff reached a stable state. There is an active core a wave at the beginning, and we let it evolve for 100 diameters. And when it reaches this mark, we reduce the Reynolds number to 1,500 by changing the velocity of the piston. So by that way, we can stretch the puff. The puff becomes a little bit narrower, a little bit, and at some point it loses contact with the wall and decays. So by doing this experiment that way, the slowing down experiment, we reproduce the probability distribution of a puff decay, and we observe a much robust data that were plotted here. These were only with 20 to 40 experiments. We could reproduce these exponents, and now the exponential decays were much more clear. Of course, these were only a limited number of experiments, and when you do 20 experiments and only one decays in front of you, you are never really sure. And in fact, this is one big miss of my work, is that some people after that come back with an experiment where they were able to do 500 and 3,000 runs of the same experiment with the same kind of idea. Measuring the pressure while the puff is passing through is only changing by 2.5 pascals, very, very accurate pressure sensor. And they were able to obtain the mean the decay rate of the puff over a much larger range of Reynolds number. And there was an article in the press at the time that to predict turbulence, you need to count the puffs. And here they've done thousands of experiments. So, to give you an idea of how beautiful is the experiment, here is another movie that we did in Japan with our collaborators that Tasaka did. So here we follow the puff, and you see the injection is from the bottom. And we think at this point that it's almost dead. But for some, these hairpin vortices that have almost the same diameter, the same length as the diameter of the pipe, was able to restart, create this hairpin vortex on the top, and initiate the self-sustained process. So this is for Reynolds number 2000. And for the Reynolds number 2300, experiments and numerical simulation have shown that the puff can split, it grows, and can change and separate, just like in some other fluid mechanics phenomena. I let the film start. So it reaches the end of the pipe, and we have to stop the film. So the Poiseuille flow enters the pipe, the puff moves slightly at a velocity slightly slower than the main flow, and it creates these vortices. Okay, so in 2011, the people have gathered together all sorts of data from experiments in very long pipes. To show that the decay rate of puffs increases as super exponential, and the spreading of puffs of slugs could also be calculated, and they find out that there is a critical crossing between these two phenomena, and that was reported in this Nature paper. And the splitting and the decaying rate, this phenomena could be modeled by models developed by Dwight Barclay. So now I want to talk about synthetic jet, because most of the experiments were done with single impulse jets. So the synthetic jet is always based on a hole on the pipe wall, where it's a very simple, well, it's a brilliant mechanical design, where you have a small cavity and a rotating motor that has some eccentricity, and that will by rotating it will press on a membrane, and that will inject vortices toward the wall. So we could see these vortices using a light box and a laser kit. And on the top right, I can see some ink. I can show you some ink where we have injected this these vortices using the synthetic jet actuator. So this disturbance is a little bit more complicated than the single jet, because we need a few more parameters. You calculate the velocity of the jet that you divide by the mean flow of the pipe, and then as you do oscillations, you need to make a dimensionless number with the frequency of the oscillations. So we call it ST or STUR, if you like. And of course, you have to, all the experiments are done with a certain eccentricity, a certain displacement of the connecting rod. One big advantage of this type of disturbance is that you can introduce a given number of hairpin vortices. For example, here I show you on the top, on the bottom right, I can show you a space-time diagram. So we take a vertical line on the pipe, we let the flow disturbance pass through, and you can count the number of vortices. This is at the position 5 diameter from the inlet, and this one is at 10 diameter from the disturbance inlet at Reynolds number 1500. And you can see how these 5 vortices will interact, and in this case, they will decay. So we tried to do experiments at different BR, ST, and different N. And for example, this is for Reynolds number 2000. We see the probability of a certain set of parameters to create a puff that will sustain 100 diameters. And we can also fix the number of waves that we introduce. So it's not very clear, but it looks like the even numbers have a higher probability than the odd numbers to create a turbulent puff that will survive. This is very much work on progress, but this is the kind of things that we could do with this synthetic jet. We've done also experiments with divergent pipe flow. So now we are changing a little bit the geometry of our pipe. So the divergent pipe flow or the expansion pipe flow is not stable for all Reynolds number. There is a linear stability limit. Theoretical studies have shown that the critical Reynolds number is about 3000 Reynolds number, 3273. But the transition is seen in these experiments at much lower Reynolds number, meaning that the finite amplitude disturbance have an effect. So my question was, can we see puffs and slugs in this geometry? And we've done some experiments. And in fact, the great advantage of this system is that this time we don't need a traveling camera because everything stays in place. But there is additional circumstances. Here we have a recirculation region in the corners, and we have a strong deceleration because the section is increasing very much. So we've done also experiments with sudden expansion. The most studied case is the 1 to 2 diameter expansion. In this case, you get a recirculation flow in the corner. In laminar flow, this recirculation in the corner increases linearly with the dimension, the axial dimension of this recirculation flow increases linearly with the Reynolds number. And one question that people ask is this system an amplifier or of the disturbances? So we introduce. So this is a picture of the experiment. This time it's a vertical experiment with a constant height water level. And the velocity is controlled by a tap at the bottom. So here is the synthetic jet actuator that is introducing a disturbance. So this flow without disturbance will get turbulent at Reynolds number 1140. According to this reference here, where they looked at the recirculation region and how it becomes unstable, time dependent. So we introduce disturbances to get the transition to turbulence. So in this graph, I show you the results for the synthetic jet. So now for this graph, I show you the disturbances for simple jets. In green is the section. Of course, when you do a section disturbance, you need a very large amplitude. You need to stack 10 times more than you pass through to get a transition turbulence. So below the green dots, the flow is laminar. Above the flow becomes turbulent. And then if you use the blue diamonds are at the transition threshold for the single jet. And then the diamonds, the open diamonds are the onset of vortices that you can see, but do not lead to turbulence. And the gray bars are the regions where you can see hairpin vortices. So we get a very different scaling. We get hairpin vortices. In this case, we do in the bottom figure, we do a section, and you see that the disturbance modifies greatly the recirculation region. You suck in the bottom, the top recirculation region increases very much and becomes unstable at the end of the recirculation. We've done some experiments with the synthetic jet. We use two different eccentricity, so vertical motion, 50 micron and 100 micron. Of course, the larger the eccentricity or the amplitude, the smaller the range of Reynolds number. When you use this synthetic jet experiment, I will show you a movie in a minute, you create a disturbance that leads to a puff, and this puff becomes turbulent and remains fixed at the position 10 diameters from the inlet, from the expansion. So here is a movie of the synthetic jet to the sudden expansion. There is a die here. So you see that the sudden expansion is very, the synthetic jet creates oscillations. This oscillation grow. And to represent the amplification of the disturbances, we take vertical lines, B, C, D. And for each line, we do a space-time diagram. So every image, we take only this line and we reconstruct this line as a function of time. And you see that as we go to closer and closer to the inlet, you see that the frequency is smaller. So when you go far away from the disturbance, the frequency is stretched. So really, the synthetic jet disturbance in this context behaves as an amplifier, and the space-time diagram suggests there is no swirling in this flow. So we've done also experiments where we added a rod in the center of the flow. So in this case, it's even more complicated. We have two Poiseuille flows, recirculations in the corner, and then if the rod in the center is a little bit bigger, you have additional recirculations along the rod because you are distorting very much the streamlines. You still have an analytical solution for the flow. You can calculate the theoretical laminar flow. You can also measure the recirculation region. So for different, so each picture here is for different annular. So the carbon rod that is inserted is bigger and bigger as we increase from A to D. And the recirculation region that is in the corner, where the limits are shown by arrows. I have some movies, but they are not so good. So, but the recirculation it grows linearly, and once the inner cylinder, the rod has a larger diameter, there is a secondary recirculation that appears, and we can also follow its growth. We can do also numerical simulations, so these are the velocities. The red is the rod in the center line, and you can see that the recirculations, the streamlines are very much curved, and from this curvature we can calculate a Rayleigh gradient that will indicate you that there are different regions that can go unstable. At higher Reynolds number, we've seen that when the rod has a small diameter, you get disordered flow. When the rod has a large diameter, then you get periodic turbulence. I will end up here, I think. So I've shown you pipe flow is sensitive to the type of disturbance that we put. Using jets or using synthetic jets, you can get amplitude curves of a different kind with different scalings, with different critical Reynolds numbers. This is often overlooked in the models. So I hope I convince you. So it's very, depending on what kind of actuators you're going to use, you can have a, and sometimes it's not injecting more that will give you a more direct response. These are very subtle effects. Also, I played with the expansion, with the effect of a rod, to show you that whenever you have a corner, creates you a recirculation that changes very much the transition mechanism. These recirculations will then interact and will reduce the Reynolds number very much. So adding a centerline rod changes the transition and can give you different types of turbulence. So in the future, we will continue to work on the synthetic jet, trying to quantify the different types of wave packet, wave numbers, to see if we can find some response that is more appropriate. And to finish, I would like to mention that we are still in a very exciting times for transition to turbulence, because now with 3D printing, some people, including Bjorn Hoff and his group, have developed objects, obstacles, injected objects that can relaminarize the flow, get the flow straight. So we could now, if we have long straight pipes, we could get a section of the pipe turbulent, another section of the pipe laminar, and these phenomena are still not very clear. I think there is some work to be done in this area, and I think we hope we can continue to work on this. So I will end up my talk about this. Thank you for your attention.
Yep. Okay, so thank you for this nice presentation and this very broad overview. So if in the room there are questions, then you can raise your hands. I cannot really see because you are all sitting in the back, but maybe I will let Jorge answer the questions. And then if some people in the online audience have questions, then they can maybe signal this themselves or ask them in the chat.
Yes, I may want to start. Can you go back to, I think this is slide 33. 30, yes, this one. I don't know if it's 33, but this. Yeah. So you are showing that the frequency of the phenomena you are observing is changing depending on the axial position, right? Yes. And this is the case where you are making an excitation with a synthetic jet which has its own frequency. And how is this the frequency of the synthetic jet? How is this value compared to the frequency you are observing here on DC and B location, and how does it change when you change the frequency of your synthetic jet? I don't know if I was clear or not.
So the synthetic jet frequency has a small number of 0.1. Maybe I haven't put everything here, but basically D is very close to the excitation, and as you move along, the frequency or the wavelength is increased. Okay. So now how does it change with the frequency? So this ST is the dimensionless frequency. So if you are below, the frequency gets, the oscillation gets damped. If you are below this curve, the frequency gets damped. And if you are above this curve, the process will get much abrupt, and you'll create a turbulent patch very quickly. So this movie that I showed you is very much on these points here. So if you are above these points, you introduce a disturbance that will grow faster and that will create a turbulence that will develop faster and will get much more disordered. Okay. Yes.
You said that you studied the pipe flow, the very beginning you said that, as a typical flow, something which you hope eventually, perhaps beyond our lifetime, I don't know when, will teach us something about all flows or generally.
Mm-hmm.
What do you think as being able to be generalized or being able to go beyond just the pipe flow?
Well,
Or were you optimistic? I don't know.
no, I am very optimistic. I think compared to Reynolds, so we didn't have this theoretical background that we have now, that we see now this streaks, rolls, and this literature where we have this syntax to describe what we see. And compared to Reynolds, we have synthetic jets, straighteners. We have some tools where we can manipulate the flow a little bit more. Of course, this is still very much empirical, I think. Well, some people are very good at it, but I think the general student population doesn't know that we can do these things. So I think this is that's why I think the synthetic jet, although it's a bit complicated actuator, because you introduce three parameters, right? The amplitude, the frequency, and the number of waves. So it's three additional parameters. So you have a complicated problem where you have three additional parameters. So it makes things very complicated in appearance, but it opens you some opportunities where we could, for example, with the synthetic jet, we can introduce disturbances at the wall or the core of the expansion. So it's not like you have just a jet or you have a jet past a cross flow. It's just we have just one type of way of getting the turbulence into the system, and then the system develops this turbulence. So here we have something a little bit more delicate and subtle to play with.
Is it to find that the outcome depends on the type of disturbance? There's no universality, really.
So what I say is that the threshold curve depends on the type of disturbance. Once the perf has survived for 100 diameter and it's in this ping pong ball regime where you go from one traveling wave solution to the other, then it's another story. But I think how you get into turbulence is very much sensitive to the way you perturb your flow. Then once you are in the weak turbulence regime, or another, call it as you want, I think it's when you are in the area of homogeneous turbulence or some specific types of turbulence, then you can, for me, this is a different field. I am just in the border here, okay? And this border depends very much on the way you enter, okay? And some people have claimed that just make a jet and you get into turbulence. This is not completely true, right?
You said that there are many parameters that can modify your disturbance, but are we able, or how we could identify kind of universal mechanism that would generate the puff actually from the disturbance from the puff? Are we able to identify some coherent structures that are at the origin of the puff, or is it really dependent on the disturbance?
Yeah, well, so in the case of single jets, you see there is the hairpin vortices that appear, and in the case of the synthetic jet, you see there is this wavy pattern. So I think there is a certain number of mechanisms or ways to get into the turbulence. Well, now these are, of course, based on visualization techniques, and each technique has its own bias. But yeah, I think there is a limited routes where we can but
Do you think that they can be classified, or
I hope-
there are many that can be classified, or there can be as many as the?
I think
parameter?
some people have tried to classify it. I'm not sure. Classification or zoology is a good science. Maybe, maybe not. I have no answer for this question, I'm afraid. So no more questions from the room? Maybe
what I'm
last
just
one?
wondering, so I'm
Yes.
asking, with the system, the device you are using to create a synthetic jet, where you are creating, let's say, some kind of coherent structures. And do you also produce some acoustic wave that could also
So in this case, this is water. The flows you've seen, the films I shown are real time, so centimeters per second. So there is no noise. I don't. So now this is for water. Maybe if you do the same experiment with air, I'm not aware about the literature on air very much, but I've known that there are some acoustic actuators. Of course, when you introduce a disturbance, the flow is incompressible. So it is clear from the picture here on the experiments in Delft. So you see, once you introduce the disturbance, whole pipe, the whole flow, all the molecules in the system will know it. So, that's maybe one of the advantages of the synthetic jet, so that you can progressively increase. There's no abrupt spike, but I don't know about acoustics, acoustic actuators. So no more questions on the room.
Are there questions online from the audience? You can unmute your mic or raise your hand or write them in the chat. No. So maybe if not, I will maybe ask a few questions. So when you go, can you go back to the slide 30 something, 33? This one here. I was a bit surprised when you said that what you observed was dependent, at least the fact that he amplified disturbances and created a wavy pattern, that you said that it was dependent. Basically, the question I have is, do you have this amplification for at least linearly for any disturbance amplitude? Or do you see, let's say, wavy laminar patterns only if the disturbance is above a certain threshold?
Yes, so that's so here on the bottom left, this is the frequency, dimensionless frequency as a function of the Reynolds number.
Mm.
And the red symbols are with an amplitude of the eccentricity of the cam of 100 microns, and the blue are for an eccentricity of 50 microns. So if you increase the amplitude of the sine waves, you'll get a shift toward the left. The movie I took, I think there are the parameters on the slide. The Strual 0.1. So basically, the movie I took is one of the red symbols.
Okay. Because what I could expect is that this, at least these oscillations, would be the result of some linear instability that basically could be seen in the especially developing flows like backward facing steps or the wake of an object, and then basically the fact that you have a wake which is oscillating would be independent on the disturbance amplitude, and would just be dependent on the fact that you have some sort of disturbance, and that it could be studied by linear stability techniques of local convective or local absolute instability, or the fact that you have a global instability mode. So I was a bit surprised that you said that if you try to go to infinitesimal disturbance, you don't see anything in after the global expansion.
Did I say that?
Because you show curves that they depend on the amplitude, and I was wondering whether you could see things that see a pattern if you have an infinitesimal amplitude disturbance.
You have a small amplitude disturbance. The curves will shift to the right, and it will eventually reach the linear stability limit. Yes. Okay. And you can get a classical parabolic shape. In fact, there is a paper by physics of fluid paper from the 70s where they use a very thin plate inside of the pipe, and they get a curved curve typical of boundary layers.
Okay, that was one first question that I had, and I think I had another one. Yeah, but when you said about the classification of let's say disturbances, because what people could think of would be, let's say, to look at the maximal to the resistivity of the flow. So, for instance, in the 90s, people were doing some non-model linear non-model analysis of the wall flows, and see that there were some structure that were linearly the most responsive to some forcing, and then they tried to do this non-linearly. So I was wondering whether this type of classification could help to try to have some optimal on some criterion or some other to try to see what is the most responsive type of structures, maybe because maybe if you try to vary the type of forcing, and that was, for instance, things done in the 90s for you take the wall flow, you put you linearize it, you put some noise, which basically can encompass or cover all type of forcing, and then you try to see what is the most responsive type of structure. And I was wondering whether this could help in doing a classification of.
Yeah. So basically, this type of linear disturbance do not work in straight pipe flow. Yeah.
But then they were
I
extended.
don't know if it will work on sudden expansion flow, but you need quite a large amplitude disturbance to.
But the thing is, a linear.
So, of course, maybe there is some disturbances we haven't thought of that will fill the gap. But I think I've done a quite big review on different types of jets, different type of. There are other types of disturbances with multiple jets, and I didn't talk about. There is a good review by Tom Mullin in 2011 in the annual review of fluid mechanics on all the different types of disturbances. I think the synthetic jet is a new one, and maybe there are some other new ones that could be tested.
Yeah, but the linear, let's say, analysis is actually relevant because it identifies the lift-up phenomenon, and basically it captures a physical effect. And in a way, even if you put an infinitesimal disturbance, it will never trigger turbulence, even if you have any kind of amplification because you have a basin boundary. But still, it captures a most, let's say, receptive type of structure. And this has also been done non-linearly, trying to find the most responsive, let's say, initial condition that would trigger the maximum amplification in full Navier-Stokes equations and all these kind of things. So maybe this kind of a criterion of disturbance or forcing of a very wide class could help identifying and then some typical routes or path to turbulence and their forcing. And conversely, even if you put infinitesimal, very tiny noise, you can still have, if you force with a very tiny noise for a very long time, you can still have the some rare situation where this noise pile up and still triggers turbulence.
So for pipe flow, usually some disturbances have been suggested in this line of ideas, but they are unphysical and unrealistic. It's like adding a wave all along the pipe. Things like this are not practical from an experimental point of view. Maybe that's why they have not been tested.
But for instance, if you put,
but they are relevant. I agree.
But for instance, if you put some noise at the inlet, maybe you can have a most responsive answer to the noise that you put at the inlet. And if you put some noise, basically you will be able to span all type of disturbance structure, because you force basically the whole spectrum.
Yeah. So how can you put noise in water?
But
the acoustic actuator then.
Yeah, it was just some using, and because what happens on boundary layers is that the turbulence is usually triggered by the disturbances that come from upstream, and basically that what comes from upstream can be to some extent viewed as noise, because you have all kind of things that arrives on the boundary layer.
So here we are in water. Most of the experiments I've shown is in water. The noise in water, I'm not sure how to introduce the right level of noise in a water system.
Yeah, maybe it's more difficult to because what we can think of when we have, for instance, we want to send a given amount of perturbation to an experiment, at least in air, is that we have some let's say some grid, and we create let's say grid turbulence downstream of the grid, and then we can to some extent think of what comes downstream of the grid as noise that would arrive to some other experiments, and then we can characterize the root mean square of the velocity in this grid turbulence, and then view this as a noise that would arrive on yet another experiment.
Yes, I'm not sure this transposes directly into my water
because
experiment.
I remember that in the thesis of Tao Liu in SPCI, basically he had some grid at the entrance of his Poiseuille flow, and in this grid created some disturbances that were traveling downstream of the grid, and depending on the kind of grid, they could characterize the fact that they had a different roots, let's say a different amplitude of these noisy disturbances, and that these different amplitudes of noisy disturbances triggered the turbulence differently.
Okay, so I understand what you mean now. So usually, so we use a pipe flow like this. So usually we have a settling reservoir, and before each experiment, to have the lowest level of noise, we wait 20 minutes or so for the disturbances in the reservoir to be damped. Of course, you can imagine to put some kind of grids into the reservoir, and then you don't need to wait 20 minutes or so for the signal, but you start from a different level of noise in the system. But how to quantify this noise?
Yeah, first, what you can see, what you can do is measure maybe a time series of velocities, and this velocity will have an average, and we'll have a variance, and we'll have other cumulants, and then you can characterize this noise by its moments, by its spectrum. Maybe it's a bit technical to do, but it's a bit
so
to do.
Usually in water, these quantities are very small.
Well, it depends on but then even if you put some very small noise at the inlet, it might be that after some time, this small noise may be able to, you may have an occurrence of this small noise that may be able to pile up and trigger what happens.
Yes, I agree, but this type of experiments in water is not trivial.
Yeah. Okay. If other people in the rooms have other questions, or in the audience, or if not, maybe we will conclude here. So we can again thank Jorge, the speaker, for these nice presentations and the answer to all our questions. And yeah, so we'll then finish for today.